we are going to discuss about binary search. So, what is a binary search and why is it used, and what are some of its use cases? Suppose we have a problem in front of us, and the problem is that we want to find a number 4 in an array 1, 2, 3, 4, 5. Correct. Now, the traditional way, the way we used to do this, if we don't know binary search, we do this linearly, and that is called linear search. And we go from I0 to n minus 1, that is 4, and we see every element at every index add I, and if x is equal to that element, then we return the index, right? So let's just quickly see a simulation of that. So how it would go is, let's take a pen. 1 at index 0, 2 at index 1, 3, then 4. And when we have found our 4, which is the target we were looking for, we would return the index, and the index in this case would be 3. Correct. And this is how we use linear search. But now we see how we do this in binary search. So in binary search, what we're looking for is the midpoint of an array, right? So how this works is we have a sorted array, say the same array we're using below, and we're trying to find 4, right? So we'll look at the midpoint of the array. We'll see the formula for calculating it, but now it's just the middle of the array, right? So if we find the middle and if there's the target we're looking for, we'll return the middle. Otherwise, we'll look left and we'll consider that as a new array and we'll try to find the target in the left. Otherwise, we'll look at the right and we'll try to find the element in the right of the array. So let's see a simulation for that too. Okay, we have mid equal to 2, so that is the middle element we've taken. We see that it isn't equal to x, it isn't greater than x, but it is actually indeed less than x. So yeah, so it meets this condition. So we'll look right and we'll try to find 4 in the right of 3. So now the midpoint of this array, though it's difficult, but we'll just take the floor value and it would be 4. So we get the midpoint and that is equal to x, so it will meet the first condition of the algorithm, so we'll just return 3, right? So as we saw both those algorithms, we can see that in a linear search it would take us 4 steps, but in a binary search it would just take us 2 steps. Now let's look how we calculate the midpoint of a binary search array. So when we're doing binary search, to calculate the midpoint, what we do is we have two basic formulas, but sometimes L can be as high as 2 to the power 31. So the first formula, that is L plus R by 2, which would be simple, gives us overflow because L plus R might overflow to just about 31. So we use the second formula, and if we do some little bit of mathematics here, we'll see that the second formula is just the first formula, but written in a style so that it doesn't overflow. Now let's look at some real life examples where people would use binary search, right? So the best example I can find is, suppose we have a group of students who all have different heights, and the principal gave the teacher a task. The task is the teacher wants to find a student who has a height of say 5 feet, right? Sorry, feet. Yeah. So let's see. Normally, if a teacher doesn't know binary search, what she might do is measure everyone's height and see which heights are equal to 5 feet, right? But a better way might be to make all the students stand in a line in their heights order, right? And then just use binary search. Okay, so we'll look at the middle element here. We see that the middle element is here, and say the height, the middle element has probably is 4 feet, right? And then, since we know with the algorithm that if it's lower than the target, then we look to the right, and in the right the middle element is indeed the one which is 5 feet. So instead of measuring almost 9 heights, okay, the teacher only measures 2 heights, and she has her answer, right? So this would be a basic way in which a teacher might try to use binary search. Next, let's discuss why binary search. So suppose we have an array, right? And in that array, we want to find a number, but we're considering the worst case, right? So we keep on dividing the array, right? And we divide it up until there's only one element left, and that is the one element we're looking for, because that will be the worst case, right? Now, at every layer, the number of elements decrease. So n by 2, n by 4, n, so on, and then we find a array which has only one element, right? So this, we can see that this can be represented as n by 2, n by 2 square, and at the end, n by 2 raised to power some number of levels. So we'll just say the number of levels is k, right? So this is the zeroth level, this is 1, 2, and at the end we have level k, right? So we want to find that how many searches, how many comparisons it took for it to reach its worst state, and that would be given by writing as n by 2 k is equal to 1 and k is equal to log base 2 of n, right? Now, this is the worst case of a binary search compared to a linear search, in which the worst case would be that we are trying to find the last element. That would take us n steps or n comparisons, right? So we see that mathematically binary search is better, but now let's try to implement binary search, right? So we'll write a recursive function, we'll pass an array, the target, the left and the right pointers, which will imply the endpoints of the array we're looking into, right? And if at any point left crosses over right, we return -1, which means that we do not have the target in the array. And then let's look at the midpoint, we'll get left plus right minus left by 2. We check if we found our target, we return the index we found our target at. Else, if the array index we are at is greater than target, then we have to look for a smaller index, right? So to look at the smaller index, we'll change the just the right value. So we'll go from left to mid -1. Else we'd go from sorry. Else we'd go from mid +1 to right. Correct. So we'll just quickly implement this binary search. We'll try to run this. We'll give an array 1, 2, 3, 4, 5, and let's just try to find a 4 in 1, 2, 3, 4, 5. The endpoints will be. Let's run it. Let's see what we get. And we get. Okay, we have to print it, and we get 3. So it was our third index. So yeah, 4 was our third index. Now let's look at the iterative implementation of binary search, which is the one we'll mostly use because this is more efficient. So we'll keep the value same for array and the target we're trying to find, and we'll start this loop. L less than equal to r is the condition. So till it's not passed on, we find the mid value. If array of mid equal to target, that's simple, we just return the index we have, which is mid, right? And if we don't find any index in that while loop, we'll return -1. But let's write other conditions. One condition would be if it's greater than target. then just like we did in the recursive solution, we'll decrease the value of the rightmost index. So that is because we have to look towards the left, right? So looking towards the left would mean r is equal to mid minus 1, right? And else what we'll do is l is equal to mid plus 1, so we have to look to the right. Okay, so we'll quickly try to run this as well. Let's see if we get our answer. And yeah, again 3, it was the third index, so correct. Now let's look at some interesting problems we can solve using binary search. So one such problem is finding index of the smallest number not less than 5. So what does it mean? It means we need to find the leftmost index which is greater than or equal to 5. Leftmost index whose element is greater than or equal to 5. So let's use binary search in this, and it's quite intuitive if we see that if we look at the middle element, is it greater than or equal to 5? No, it is not. We'll need to look for more rightmost elements. So we just pick that array up 6, 7, 10, 11, and meanwhile we are also keeping temporary variable answer to keep track of do we have a answer yet, correct? And in our second iteration we'll have an answer when we go to the second midpoint which had an index 5, and we'll store it because it is greater than or equal to 5, correct? But we still can look for a smaller number, right? So we'll look to the left. The only array left is now just 6, correct? So in that 6, the middle element we have is 6, and the index for that would be 4. We'll update the answer again because it's still greater than or equal to 5, so answer is equal to 4. And now after this point, there's no array left, correct? So what we'll do is we'll return answer equal to 4, right? Now let's see and let's realize that why is this of such importance, why is this problem so interesting, is that in this case we had a scenario in which the values for the array can be represented in a boolean compared to 5. And if we compare it according to the statement, are these numbers greater than or equal to 5? So that will be no, these numbers are not greater than or equal to 5, so that will be false. These numbers are, so they'll be true, correct? And this is very useful in binary search. A lot of times in binary search, we use arrays which are not exactly sorted, but they have a monotonic flow about them. That monotonic flow can be that they are false till a certain point, and after that they are true. And we'll just find a border. We'll find the last false of the first two for binary numbers, correct? For in that binary search. This kind of binary search in which you find the smallest number greater than or equal to a number is called lower bound, and we'll try to implement lower bound. So let's get into the code. So we have a function lower bound over here, and we have an array, a target, left and right endpoints. Let's just quickly name a variable answer which is -1 in case there's no index greater than or equal to the particular number we're trying to find, and we'll find the midpoint l plus r minus l by 2. If array of mid is greater than or equal to target, we'll keep looking left for a smaller number, but we'll simultaneously update our previous answer too, right? And else we'll just keep on looking right and then return answer, correct? Let's run this quickly. It's 3, yeah, third index is 4, which is the smallest number that's greater than or equal to 4, correct? But if we're just looking at the greater than numbers, that is index 4. And when we're just looking at greater than numbers, that is called upper bound, and these are very useful for C++ people. Next, let's talk about finding the square root of a number. So this question, it doesn't include any array, but we see that the root of 16 lies somewhere between 0 to 16, right? So suppose this x is the root, correct? And now from observation we can tell that every number between 0 to x would have a square, so like that element's square would be less than 16, and every element's square from that root to 16 would be greater than 16, right? So we can use this observation to our advantage, and suppose we set greater than 16 as a comparator, we see that all the values for this part would be false and all the values in this part would be true, correct? So we'll see that this point, this is the separating or the bordering point, right? So we need to find the last false or the first true, or actually in this case, because this is an integer value, we'll get an integer root. We just need to find that equal to, right? But if we wanted to find a real number, and how we'll implement this is we'll go to the last false we get, okay? And this is similar to how we did it in lower bound. In lower bound we wanted to find the last false, which means the last value which was less than 5, right? Or which was not greater than equal to 5. So this bordering values is what, finding this bordering value is what is binary search good in. So we'll try to implement this. We define a function root. We keep the left endpoint as 0, right endpoint as the value n itself, right? And finding the mid is same. But the condition is that the mid and n, we'll just define a condition in here, but the condition we all know is that the mid's square should be greater than n, as we discussed. Okay, so we'll define a condition here really quickly. So if we have an element and element square is greater than 16, then we return true, and if it's less than 16, then we return false. So in this case it's less than n, we return false. If it's greater than n, we return true. So this set, and we'll quickly run it, and we see that we've gotten our root. We'll just quickly prettify it to root of this n is this, so we'll get the root of 16 is 4, right? Now let's discuss another very interesting problem, which is a rotated array problem. So in this problem, what we look is, we look for a pivot. So what is a pivot exactly is a point at which the array was rotated, right? So here you can see that 4, 5, 6, 7, 8 and 1, 2, 3 has been rotated at index 3. So if we take 1, 2, 3 to the start, it will be a completely sorted array. So you'll notice that this array is not sorted, but we'll still use binary search here too. And why we'll use binary search is similar to the idea of using binary search in lower bound or using binary search in the root problem, and that is if we have true true or false false values, we can always find the bordering value, right? So in this case too, we'll try to find a comparison which we can use to make half of it either true or false, and then we try to find the last true or the first false. Okay, so let's go ahead with this, right? So as we discussed, this is not sorted, so how will do this? So okay, let's get on with it. We have a function which we'll use, and that is that if this is the left element and this is the rightmost element, and we have a middle element, if we compare the middle element, okay, the an with ar, the rightmost element, we'll, from my handwriting, yeah, ar, we'll get a condition which will be true till 8 and then false. So we'll get the bordering condition, and then we can find the first false, right? So this will be all true and this will be false, 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 and then we'll just implement a function, implement a binary search to find the first false. Okay, so uh, let's quickly look at the implementation for this. So we have the root function already prepared. It was quite similar, but in the root function, And in the lower bound function, what we were doing is we were trying to find the first true. In this, we'll do a little bit of twist and we'll find the first false. Okay, so we'll change the condition if mid is greater than high. So as we discussed, if mid is greater than the rightmost point of the array, then we'll return false, or even equal to. This equal to is necessary in case we have uh, 3 in start. Okay, so we'll change the find pivot function, define pivot as 0, because if we don't find any pivot, then the array is already sorted, right? And yeah, we'll check the condition. If it's true, then we go change the pivot. So we got our answer 5. So let's just simulate this once. We looked at the middle element. We saw that this was greater than the array high, so we move towards the right, correct? Then we again look at the middle element, which was 1. We see that this is not greater than the rightmost element, that is, it is not greater than 3, so we move to the left, but we include this element in this case, right? So in previous case, it was true, we were looking at 7, and in this case it was false, so we took left with the element. And in this case also this is true, so we'll take right without the element included, correct? And we have just one element left in our array, that is 1, and that is our solution indeed. So this index, we are dealing with everything in here as an index, so we'll get 5 index